Okay, so now what we're going to talk about is linear regression. Okay, so I need to use my pen, if the data are correlated, then do a linear regression. Okay, so the rule of thumb at this level is if R is between -1 and -0.5. Okay, if you don't know what I mean by that, like as an example, I mean -0.86, like the example we did last time. If R is between 0.5 and 1, that would mean, like, example, R is, I don't know, 0.72. Then there is strong enough evidence that the data have a linear relationship and therefore you can perform linear regression. Okay, so what we need to talk about is, let's kind of do it. What is linear regression? Okay, so if I have a scatter plot like this, and here's X maybe, and here's Y, and here's my data. Okay, that looks linearly correlated. What we're going to do is we are going to fit, okay, we are going to fit a line to the data. And that line is called the line of best fit. And that line of best fit is denoted by y hat equals A plus beta x. Okay, so it looks, I think I just said beta, but I meant B. So what this is these are the, what we call the predicted values, and X is the actual data value. Okay, so I need to explain, like, graphically what's going on. I'm going to switch my color here to blue, and I'm going to take this point right here. Okay, that point right there has a coordinate of X and a coordinate of Y. Here it is. I can't get right on it with my fancy. My monitor is awesome, but not that awesome. Okay, so what I'm going to do is the point that's actually on the line, that point is y hat. So it tracks over here to y hat. And the distance between the data point between data value, which is y, and the point on the line and the predicted value, which is y hat, that is called the residual. So there's some crazy math behind what's going to happen here. But what we do is the line a best fit minimizes. That's a big word in math. We love to minimize stuff. Not minimizer, minimizes. Minimizes the residuals. So we're trying to figure out a way, in fact, to cancel them out. So the one that's right here might be the same length as that, but since that one's above and that one's below, they cancel each other out. If this one above here and this one below cancel each other out. This one that's really close to the line is like maybe matches that one, they cancel each other out. So we try to put the line in such a way that it cancels it out. And of course it has pretty nasty, horrible looking formulas, because if you can imagine that to be happening in real time using real data with perhaps an infinite amount of data sets, it's going to have, or data points, it'll have some pretty insane formulas for it. So I want to talk about those. Okay, if the line is given as y hat equals a plus b x. If that's hard for you, just remember from all your previous math that this is just mx plus b, all right? Where b, in this case, is the slope right here, right, which is very different from that b. So way to have algebra and statisticians not want to talk to each other about certain concepts, like the way we label stuff in textbooks, but regardless. M and A is the y-intercept. So it's just the exact same equation for a line that you have been working with since you were in the 7th grade. So don't be afraid of that. Now the problem is the way we find that. B is calculated to be that regression coefficient times the standard deviation of y over the standard deviation of x. And if you remember that our equation is therefore, I'm going to put the sy over sx out front because multiplication is commutative and I can move it back and forth. So sx times, and if you remember what r is, it's 1 over n minus 1 times the sum of the standard errors, which is x minus x bar over sx times y minus y bar over sy. So that's the true formula for B, and of course this is trying to minimize those residuals. We will not compute lines of best fit by hand in this course since we have all these fancy tools. We'll let the fancy tools do their job and understand what the line means, not exactly can we compute it. All right, where A has a different formula. Of course, this is the y-intercept, and it's found by taking y bar, and then you subtract off b, the slope of the regression line, times x bar. Okay, so that's how they're found. Now I want to move into some software so we can kind of see it happen in StatCrunch. So I'm going to move to StatCrunch, but my mouse is all tangled. Here we go, StatCrunch. So there it is, and we've done quite a bit. Let's just pull up the graph again, write the graph of the scatter plot. The x is the weight of the variable, y is the mileage, and I look at the scatter plot. And so what I'm going to do, it says I can save it, do anything I want with it. So you can put this into a Word doc or a PDF or whatever you want to do. And what I'm going to do is not that, is basically draw a line that fits through this data. All right, so we're going to go through that process right now. I'm going to move this over here. What you do is to stat, and you can look through there and you can see that one of the options is regression. Okay, now it says that there's simple linear, polynomial, multiple linear or logistic. We are only going to be dealing in simple linear in this class. If we have time, I will do some multiple linear because that's what you're actually going to see in the real world more often. But we need to just understand how the simple linear works. The x variable is the weight, the y variable is the mileage, and we're not going to be doing any hypothesis tests or things like that, or confidence intervals, but we may be able to do a prediction, okay? So let's do a prediction of one of the data points, okay? I'm going to move here, and I'm going to do the prediction at 2590. So I'm finding one of those data points, and the level of 95, just keep that as well as it is. And I'm going to compute it. Okay, so here it comes up. And I somehow have to get this to, there we go. Okay, and what you can see is the intercept of the line being 45.64. All what that means is if I was to make this graph bigger up here, right, if this is 35, here's 45, it's going to cross somewhere right there, right? And the slope is steep, right? That's a steep slope, which we expected it to be steep. So that slope is coming down, and if we write the equation of the line from there, we get y hat equals the intercept 45 point, I'm going to just call it 45.65 minus 0.005x, and that is the line of best fit. Okay, now the other thing that came out, there's a lot more that came out here. Okay, we will talk about all this stuff sort of in a future time, but right now what this says is that this is a good line. Okay, these p-values being really tiny is telling me good line. This, you should have done a linear job. It's good. And so if we go back here, we can go down here, and there's a lot of information here. Again, this p-value is telling me it's a very good line. We're happy we fit a line to it and not, let's say, a parabola. So the predicted value, notice here's my data set and my data point 2590, and 2590 predicts to be at 32.12. The actual data point is at 38 right here. So this residual, did it calculate the residual? No, it calculated the standard error of it. Okay, so the residual is going to be 38 minus 32.12, etc., which is equal to 5.88. That's what the residual is. So if I go back to the graph, what that means is here at 2590, it's this data point right here, that the distance between that data point and the line, the point on the line my line is a little, it's because I drew my line, but regardless, this point right here is 38, and the point on the line should be the 32.12. Therefore, that distance between is the 5.88. The distance is below. All what that means is that the distance will be negative because it's below the line. If you can see here, this chart that gets pushed out by the software when we perform the regression, it gives us a whole bunch of information. we're not really ready to talk about all these p-values and things like that. Just note that when you have a really tiny p-value, that means you usually matched your hypothesis. Our hypothesis was that there's no doubt that this had a linear relationship and that we should try to fit a line to it. This p-value tells us, good job. You had a right hypothesis and you should have fit a line to it. I want to use a data set now where we should not be fitting lines because it's not linear. So if I go here and I open up another data set, okay, here's another one, and I want to look at maybe this is eBay data, and here's the price of the item on data and maybe how many bids the item had. If we go to graph and we look at that scatter plot, let's look at the number of bids, the price of the item and the number of bids it has. We compute it. You can see here it doesn't look as linear as the last example. So we may not want to fit a line. Let's go to the summary statistic and look at the correlation. We're looking at the correlation between the price of the item and the number of bids on the item. And you can see it does not really have very high correlation. So this has what we call weak correlation. Since it has weak correlation, if we do an actual regression on it, which I'm going to show you the relationship here. So if we have weak correlation and we close that and we do a regression, we do a simple linear regression on the price of an item and how many bids it has. I don't really want to do any prediction or anything. What we can see is here is that, is that no doubt it made a line. Okay, there's the intercept. You can see the intercept. The intercept is up here at 39. And it fit a negatively sloped line through that data. If you look at this data, you might not have even thought it had a negative trend. In fact, I would have thought maybe it had a positive trend. Remember that the correlation coefficient, which is right here, was negative. So it did have a negative trend, though fairly weak. And you go here and look at this p-value, you can see this p-value is bigger. That means you should not fit a line to this data. This data is non-linear. Oh, I don't know what just happened there. Okay. So basically, I would conclude this data if it's non-linear, don't do regression, especially linear regression. You can do regression so that we have polynomial. I'm showing you a price and the number of bids. This means this poly order means that I'm going to fit a quadratic model. So it's going to try to fit a plus bx plus cx squared model. If we watch it happen, we can see that, again, not good model. A good model has a p-value less than 0.0001. So we will talk about those p-values, but I just wanted to run through some sort of more detailed examples than what is located in your textbooks.